cycle is less than 180 degree, but the efficiency is 75%. In case of your class AB amplifiers, now class AB is in between the class A and B amplifiers, so the operating cycle for class AB amplifiers is 180 degree to 360 degree, and also the efficiency is between 25% to 78.5%. Now considering all these amplifiers class A, B, C, a main point to be observed is the collector dissipation curve. This curve is necessary for the working of your amplifiers, as it decides the operating limit or operating range for your amplifiers. Here the collector dissipation curve is drawn. Here we are having the curve drawn between the collector current IC and the voltage collector to emitter voltage, labeling the different regions, saturation, cutoff and your active region. For the proper working of your amplifiers, the Q points should be in this region so that it can work. Now when current flows through the collector of a transistor, some power is lost at the collector junction, that is known as collector dissipation. We have discussed what is the collector dissipation. It is the loss of power in the form of heat. Now this power is expressed as, if we want to consider the loss of power, it can be expressed as VCE into IC. Your collector to emitter voltage at the output and the current at the output is your collector current. Now where P total is the power lost at the collector junction and VC and IC are the RMS values. Since maximum power that a transistor can dissipate without overheating is constant, therefore we can consider that VCE dot IC is equal to constant. This term is constant. Now this VCE dot IC equal to constant provides a hyperbolic curve. A curve is plotted as per the equation of the output characteristic of the transistor, and it is termed as a hyperbolic curve. The hyperbola curve is called the collector dissipation curve, which we have shown before. The curve represents the actual operating region for the transistor. The region left of the curve is the operating region, and that is marked. We have discussed it that for the proper working or for the operating range of your amplifiers, it should work to the left of this curve. Thus the load line selected must lie below or to left of this curve. If IC and voltage lies to the right of this curve, then the collector dissipation of transistor will exceed the unperceived limits, that is the limit provided to the circuit, it will be exceeded. This will lead to the destruction of the transistors due to overheating, and your Q point or the operating point can also be varied. Now push-pull amplifier, your next topic is the push-pull amplifier. Now what is the need of a push-pull amplifier? We have discussed class A, class B, class C and class AB amplifiers. But in class A amplifier you are having the linear output. The output is the exact replica of your input. There is least distortion. But the problem with in case of class A amplifier is that your collector efficiency is very low, or the efficiency is very low in case of your class A amplifiers. And in case of class B amplifiers, you are having maximum distortion, but the advantage over class A amplifier is that you are having the higher efficiency in case of your class B amplifiers. So if we need that you at the output you should have a higher efficiency, and that is not provided by your class A amplifiers. So the answer to this is the push-pull amplifier arrangement. In class B amplifiers, it works for your half cycle, positive half cycle. So we've modified that class B amplifier that it work for your half cycle, and another circuit of class B amplifier is employed to work for another half cycle. That is, one will work for positive half cycle and another will work for negative half cycle. And at the output we will have a complete input signal for positive and the negative, and with the higher efficiency that was not provided in case of your class A amplifier. This will be discussed in detail now. In class A amplifiers, it suffer from poor efficiency. Therefore, class B amplifiers which have higher efficiency are used at the output stage in push-pull arrangement. It is called push-pull arrangement because during first half cycle, one transistor is conducting, that is pushing, and other is non-conducting state, that is pulling. First consider this diagram. Here we are having two class B amplifiers. Here this is transistor 1 and transistor 2. Input signal is provided to the both the transistor through this driver transformer, and it due to the transformer action, equal voltage is provided to both the transistors. At the output also we are having a transformer that is connected to the load. The battery is common to both the transistors, transistor 1 and transistor 2. The concept of this push-pull arrangement is that during positive half cycle this transistor will be on, it will be pushing, and this transistor will be off, it will be pulling. But during negative half cycle this transistor will be on, that is pushing, and this transistor will be off, that it will be pulling. That is push-pull amplifier. Whereas coming to the detail, whereas in the second half cycle the state of two transistor is reversed. In the circuit no biasing is provided for two transistors because two transistors are to work in class B operation. We have considered and observed in class B operations that as IC is equal to 0, so no biasing circuit is needed in case of your class B amplifiers. In this operation, operating point is set at the cutoff region for which no biasing is required. So we are having two class B amplifiers that are joined together to work upon the complete input cycle, one for half positive cycle and one for half negative cycle. That is, for the positive cycle your this A and will be working by circuit arrangement that two transistors are placed back to back. Both transistors are operated at class B operation, that is collector current is almost 0 in the absence of the signal. The input signal is given to the circuit from driver stage to driver transformer. Secondary of the driver transformer is center tapped, that is it supplies equal and opposite voltage to the base circuits of two transistors, that is transistor TR1 and transistor TR2 are provided with the equal supplies and voltages by the transformer. By designing proper turn ratio of the output transformer, suitable impedance matching is obtained. We have considered this impedance matching and the turns ratio in your previous lecture of a multi-stage amplifier. Impedance matching is obtained to get maximum output across the load. During positive half cycle and A becomes positive and B negative, that is transistor TR1 is forward biased and transistor TR2 is reverse biased. Current will be conducted through transistor 1 only, and transistor 2 will be in cutoff state and will not conduct any current. Therefore, first half cycle of signal is amplified by transistor 1 and appears in the upper half of the primary of the output transformer. But during the negative half cycle and A becomes negative and B positive, so now the transistor 1 will be reverse biased and transistor 2 will be forward biased. The current will be conducted through transistor 2 only, and the transistor 1 will be in cutoff state and will not conduct any current now. Therefore, the second half cycle of the signal is amplified. Now this second half of the signal is amplified by transistor 2 and appears in the lower half of the primary of the output transformer. Thus in this push-pull amplifier, your positive half cycle is amplified by transistor 1 and the negative half cycle is amplified by transistor 2. The center tap primary of the output transformer combines the two halves of the cycle, that is positive half cycle and the negative half cycle, and forms a complete sine wave output in the secondary. By proper impedance matching, maximum power can be transferred to the load, that is can be taken as a loudspeaker or anything else. Now advantages of your this push-pull amplifier. As we have discussed that class B amplifiers are used or class B operation is considered in case of your push-pull amplifier. So collector efficiency is high in case of your push-pull amplifier. A distortion free output, as your output is having a linear relation with your input, you are having least distortion in case of your push-pull amplifier. More AC output power per device. Tendency of core to be saturated is eliminated in this, and it requires less ferromagnetic material. Now the disadvantage for your class B amplifier is that two identical transistors are required. Now considering this line in a basic detail, that if a same manufacturer provides you the two transistors with the same specifications, but practically that transistors can also differ or vary in some specification with respect to the voltage or with respect to the current. So it is very difficult to have the two identical transistors in case of your push-pull amplifier for this operation. And it requires equal and opposite voltage at the input, that is both the transistors that is connected at the input transformer winding needs the equal and opposite voltage, but practically it is not available. And if the parameters of two transistors differ, there will be unequal amplification. That is, if practically there is no identical transistors present and both the transistors differ with their parameters or the specifications, there will be unequal amplification at the output. That is, positive half cycle will be amplified with the differ parameter and negative half cycle will be amplified with the different parameter. So unequal amplification is provided at the output. Now complementary push-pull amplifier, this is the last topic of this chapter. Complementary push-pull amplifier is a further modification of your push-pull amplifier. In push-pull amplifier, the disadvantage was that one battery provides to both the transistor, but equal supply is not provided to the both the transistors. In push-pull amplifiers, two center tap transformers are required also at the input and one at the output. This is also the disadvantage of your push-pull amplifier. But in complementary push-pull amplifier, no center tap is employed. That is, center tap is vanished in case of your complementary push-pull amplifier, and otherwise it works on the same principle as that of your push-pull amplifier. That is, for one cycle, one positive half cycle, your one transistor is working, and for another half cycle, your second transistor will be working. But the two transistors used here in complementary push-pull amplifier are complementary to each other. That is, if one is NPN, the another is PNP. That is, complementary transistors with symmetrical circuits are employed in case of your push-pull amplifier. This is the basic diagram of your push-pull amplifier. Here, these two transistors are complementary to each other. See, here we are having a NPN transistor, here it is a PNP transistor. We are having output transformer, center tapping is vanished in case of your push-pull amplifier. For positive half cycle, your one transistor works, and for negative half cycle, the another transistor works. That is, push-pull principle is same as that of your push-pull amplifier, but the difference lies that we have provided the different batteries for both the transistor. In your push-pull amplifier, there was a common battery for both the transistors, but here we are having two different batteries for transistor TR1 and for transistor TR2. Output transformer is employed for impedance matching to get maximum output across the load. The input signal appears across the terminal AB, and similar to push-pull amplifier, during positive half cycle of the input signal, transistor T1 conducts current while transistor TR2 doesn't conduct, that is, it is in pulling state or it is in the cutoff state. During negative half cycle of the input signal, the transistors will be vice versa, that is, another valve will be pulling and another valve will be pushing. That is, transistor T2 conducts current while transistor T1 doesn't conduct, as it is at cutoff state. Hence, transistor NPN amplifies positive cycle, whereas transistor PNP amplifies the negative half cycle. Now, the amplified signal appears across the primary, which is transferred to the secondary to the load due to by the transformer action. The advantages of your complementary push-pull amplifier is that center tap transformer is not required, that was required in case of your push-pull amplifier, and weight and cost is less as center tapping is removed in case of your complementary push-pull amplifier. The efficiency is high. The disadvantages are that difficult to get pair of transistors having same characteristics, that is, NPN and PNP complementary transistors having the same characteristics and specifications. And another disadvantage is that we require two batteries of half the voltages. Now, summing up your large signal amplifiers. Large signal amplifiers are basically your power amplifiers, which work with help of your power transistors. Now, large signal amplifiers provides your power amplification, but in practice, your power amplifiers do not provide the power amplification. It is just a converting principle of your physics, that it converts your DC supply that is present in the circuit to your AC supply at the output, and the efficiency according to your this is PAC upon PDC, as at the output you are having your AC signal and the input you are having the DC signal. The amplifiers, power amplifiers are classified accordingly, class A, B and C amplifiers, and further modification are given as class push-pull amplifier and complementary push-pull amplifiers. But power amplifiers are needed so that your output load can be driven very efficiently. That is, your input power is equal to your output power. Efficient impedance matching is provided in case of your power amplifiers. So, power amplifiers are needed in case that you want that your output should be driven very efficiently. Thank you.